So in this video, we're going to look at examples of using the summation formulas in a linear example, or an example where the indexed variable term is linear. So in this case, we have the sum from I equal 1 to 6, and we want to use the summation formulas instead of writing explicitly the terms of the series in order to evaluate it. I'm calling this a linear example because this indexed variable term on the inside is linear in the sense that the variable isn't, the variable I is to the first power. In other words, think about that interior term as being like a 2x plus 1. You'd recognize this as a linear function. So this indexed variable inside of here is linear in nature, and so what we're going to do is use our summation formulas to evaluate this rather than explicitly writing out every term in the series. So what I want to do is look at this and recognize that I have the sum of two pieces. So the summation formulas that were included in your homework assignment are shown here on the side of the screen. And you want to look at this one. This one says, hey, if I have the sum from I equal 1 to n of a sum or difference of two indexed variable terms, we can separate them into individual summations. So we can take this summation here and separate it into the sum from I equal 1 to 6 of 2 times I plus the sum from I equal 1 to 6 of just 1. And then I want to focus in on this one. This will correspond to this summation formula here, where it says if I have a constant times an index variable, the constant can be factored out of the summation. So we get the constant times the sum of just the indexed variable. So this 2, which is a constant, can be factored out of the summation. So this is 2 times the sum from I equal 1 to 6 of I plus the sum from I equal 1 to 6 of the constant 1. So now when I look at this, I am ready to apply the summation formulas that I see down the side of the page. So in particular, we want to notice that in each of these we have an n as the upper bound of summation. So in this case, because the 6 is in that upper bound position, our n is equal to 6. And in the formulas, anywhere you see an n, you'll replace that n with the 6. So here I'm going to get 2 times, and then the sum from I equal 1 to 6 of I'm going to focus on the summation here, where I'm noticing that I have 6 in that upper bound position. And this says, hey, you can take the upper bound times the upper bound plus 1 and divide it by 2. So I'm going to get 2 times the upper bound is 6. So I'm going to get 6 times 6 plus 1 is 7 all over a 2 plus, here I want to notice I have the sum from I equal 1 to 6 of a constant. And summation formula number 1 says if I have a constant inside of here by itself with no index variable term, then I'm just going to get the constant times the upper bound of summation, so c times n. In this case, my c is equal to 1. So I'm going to get 1 times n, but n is equal to 6. And now I can just simplify. 2 divided by 2 is 1. 1 times 6 times 7 is 42, plus 1 times 6 adds up to 48. So here we were able to calculate this sum without having to explicitly calculate each term that showed up in the summation.